used, the most used are the L2 and the LM. Everybody's okay with this? Alright, since the signals or the integral here is looking to all possibility of time from minus infinity to infinity, of course the time cannot be negative, so we are going to make the integral from 0 to infinity, assuming that from minus infinity to 0 is 0, right? This is the causality theory. And most of the signals are defined up to a certain time t. We are going to define what we call the extended space. So the extended space is a space that will take a signal up to time t, and then it will increase it by 0 later on, right? So the system is defined up to capital T, from capital T up to infinity, it will be 0. So if I have a system that finishes after 1 hour, I will say this is the integral from 0 to infinity, but we have from 0 to 1 hour, and from 1 hour to infinity it is 0. Right? This is the extended space. Alright, so this is the definition of extended space. We say if X is a normal linear subspace of Y, then the extended space XE is the set of all signals belonging to Y, such that X and star T, so X extended by zeros, will belong to X for some fixed value of capital T positive. The second definition that is important for us is what we call the gain of a nonlinear system. So now, and this is very important, what we are seeing does not only apply to linear system, it can apply also to nonlinear system. This S, the mapping that we have from X to X could be a transfer function or it could be a nonlinear transformation. I gave you the transfer function as an example, but it does not have to be a transfer function. So we are saying that the system gain, or if I look to the extended space and I would like to define what would be the gain of a particular system, then the system gain will be the sum over all the input U belonging to the extended space of the norm of the transformation or the mapping of SU divided by the norm of U, right? So this is the output or the projection of the signal, or mapping of the signal from X to X, and this is your signal or the original signal that you are getting. The norm that you have here can be any one of these three that I have shown, or any norm that you can define and you can verify the norm properties. Now the sup means what? Means that you have, so this is the sup is the minimum of the max. So you take all the elements that are limit of your signal and take the smallest one of them, right? So if I have, for example, I have 3. After 3 there is 4, 5, 6, 7, 8. All of them are superior to 3, but the sup will be the value of 4. It comes immediately as the minimum of all the set of the set. So this is why we are saying here that the gain of our system will be the smallest value, such that the gain or the norm of SU, the transformation using S, is less or equal to a certain gain that depends on this on the system itself, multiplied by the norm of U. This is the gain of the system. All right. So basically, if I look to the transfer function applied to U, and I would like to look to what will be the gain of this of the system, it will be the gain of the transfer function multiplied by the norm of the input. So this could be the norm of the transfer function for all the frequencies. Then if I would like to see what would be gamma of S, it could be the value of gain K in steady state, the constant that will be the one that will verify all the gains of the system there as a function of a constant, a function of W's. So what will be the Bibo stability? Stability from input to output point of view. So we are saying a system that is bound has bounded input, and then bounded input means that it has a norm, and this norm is finite. So here the definition is in L2, but it could be L infinity or LP. The system has a bounded input and bounded output stable if any L2 input signal gives an L2 bounded output. Right? So any finite based on your norm gives you another finite based also in the same norm. So we are saying that a system is Bibo stable This is a necessary condition if it has a bounded gain. So if the system has a bounded gain, then the system is bounded input. It's necessary, but it's not sufficient as a condition.
The
Yes?
system gain, you mean DC gain or?
It's the, I will say it later, but it could be the transfer function itself. The body diagram, right? Remember body diagram when we talked about the semester? So if take the amplitude of the signal, not the phase, the amplitude of the signal as function of the frequency, this is your gain.
Yeah.
At each frequency you have a certain value, right?
Thank you.
Certain gain. So this is the small gain theorem. Basically, the small gain theorem, it says the following. It says, suppose that you have two systems, H1 and H2, one in the direct path, the other one is in the feedback path. The small gain theorem says that this closed loop system, we are not talking about transfer function here, we're talking about any type of system, it could be completely nonlinear. The system in closed loop is bivostable if the gain gamma 1, which is the gain of H1, and the gain of H2, if you multiply them together, they are strictly less than 1, right? And the gain of the closed loop system, the whole closed loop system, it will be gamma 1 divided by 1 minus gamma 1 multiplied by gamma 2. Right? So here the feedback that you have and the value that you should not exceed of gamma 1, gamma 2 means that you have gamma 1 over 1 minus gamma 1, gamma 2 positive, basically, in terms of gain. Right? Or the same sign as gamma 1. This definition applies to any type of system, either nonlinear or linear. So basically, we are looking to the gain of the system, and you are trying to see, based on the gain of the system, how we are able to ensure that the system in closed loop is stable.
So what impact has the extended space on the stability of the system?
Nothing.
I didn't understand about the extended space.
The integral is from minus infinity to infinity, and your signal is defined only up to t. So in order to be able to apply the integral up to infinity, you need to extend the signal. What happens up to t?
What happens up to t?
Yeah. So I think it's 0. Since the area under the curve will not change if you assume it's 0. Is it clear what this is?
Yes.
So if you look at it like this, huh? So my system is like this, up to here, capital T. But my definition is from minus infinity to infinity. Before we know it is 0, or assuming that this causality is 0. So what happens here if I integrate up to infinity? So we are assuming that this could be 0. This is the extended space. So this is x, and this, the whole thing, if I put it in red, this is x extended. Is it clear? Alright, so what we do with this, and this is the most important part. Here we have a couple of definitions, and this is what we are going to introduce in terms of passivity. We're talking about the integral from minus infinity to infinity before. So in terms of norm, now we are integrating from 0 up to infinity. We are looking to causal systems. Everybody's okay with this? So we are saying x, y bracket. So this is a function or an operator. It's equal to the integral from 0 to infinity of x of t, tau, whatever s here is a variable, it's not a system, x of s multiplied by y of s, right? Which is according to our extended space. It's the same thing as the integral from 0 to t of x of s, y of s, because after that, after t it is 0. Okay. So we are saying that the system is passive, and it has an input u and output y if this integral is positive. Alright, positive or equal to 0. Then the system is passive. A system is called input strictly passive if this same thing, y bracket u, so this is your input, this is the effect of the input through the system or the output, is bigger or equal to epsilon, a constant, multiplied by the norm of the input squared. Right? And the system is output strictly passive if the same integral is bigger or equal to epsilon multiplied by the norm of y squared. Everybody is okay with this? Any question about this? Yes.
What does this mean physically?
What? We will see what does that mean physically. Let me progress a little bit, and then we will see what it is. In practice, it means that it either dissipates the energy through the input or through the output. This is the passivity. There is no accumulation of energy in the system, but we will see it later.
And so from the first definition, is y upon u.
Y bracket u, yes.
So it's a transfer function, right?
What's the transfer
Y
function?
divided by u.
Y and u are signals. Here, all what I'm seeing is signals.
Y is output signal and u is the input.
Y is the effect of the input u through the system. Yes, it's the output
Yes.
from the system. But they are both signals.
Yes, they are both.
For our system, since we are looking to systems, then u will be the input and y will be the output.
They both must be greater than 0. Or,
Why they have to be greater than 0?
so it's a definition. Greater than or equal to 0. It's positive.
The integral is positive. The multiplication of both are positive. So either positive or either negative, both. So a system is positively like this, right? If I have a resistance and I look to the current and voltage as an input, then if I put the voltage positive, I will see current positive. If I put the voltage negative, I will see current in the other direction negative. If I multiply u times y, it will be always positive in both directions. So the integral will be positive. You understand what I'm saying here? So it's clear now? So we see here the u times y in terms of physics, for us, voltage times current is power. If you integrate the power, it will give you energy. Energy, right? So we are saying here, this is the power flow. Resistor is always with power that is positive. Either if you change the signal, the voltage is changed also the direction of the current. So the integral will give you something positive. Resistance, yes.
Professor, you mentioned that it can be passive through input output.
I just explained to him, I will come back to this. Okay? I'll give you an example about this.
My question is how to dissipate through input.
This is a very good question. So your input is not accumulating energy basically. When you are putting input to the system, you have no accumulation of energy through your input, through your system. We'll see some examples of that later.
Like an egg?
Huh?
Like an egg?
Like what?
An egg?
Lake.
Lag.
Lag. We'll see some examples. Alright? We'll see how it is. So if you try to see all the energy that you are trying to through the system, through the time, from your input times u, you'll find it equal to the input. So we are saying the system is dissipating all the energy that is getting from the input. You understand what I'm saying? You'll see it later. All right, so these are examples of relationship between u and y, and intentionally we have a relationship that is nonlinear. So you can see the signal is defined for negative u and also has negative output y. But when you look to a negative input, you have always a negative output from it. So if you see the area under the curve, it's always positive, right? This one is exactly the same, right? So here we have u and y are the same signal, have the same sign all the time. Here it's not passive because you have a change of sign, right, inside the system. So your integral, depending on where you are looking at in terms of time, could be negative. Right? And then you are looking to positive integral to the curve. Now we go back to what we have done before. We talked about positive real functions. You remember what positive real function is? We did this before. We did this last week.
Yeah.
What is positive real?
If we S equal alpha plus BJ and apply G plus.
So if we take S equal to A plus B times J, this is the Laplace transform variable,
Yeah.
and I take G of S, and I take the real part of G of S,
Well,
and then I will show that this is positive, then the system is positive real, right? Strictly positive real if I take epsilon G of S minus epsilon, and I take the real part of this, then I will find it bigger than or equal to epsilon, which is strictly positive, right? So this is a strictly positive real, and this one is positive real. And then we have done some example this time. We went and we replaced S by A plus B times J, and we evaluated the norm, blah blah blah. Now this is another theorem that links the stability. Your friend talked about this last time. So here it says the following. It says a function or transfer function G of S with real coefficient is positive real if and only if, so this is both directions, right? If it's positive real, it verifies this condition. If it verifies this condition, then it is positive real. So I'm saying the first thing is that the function has no pole in the right half plane, which means or stable. If the poles are stable, then this condition is verified. I is verified. The second condition, the function has poles on the imaginary axis. If the function has the poles on the imaginary axis or at infinity, they are simple poles with positive residues. Right? You remember what a residue is from your undergraduate program? Right? The residue of a pole is the value of the constant, where if you make a partial fraction, for example, you will find it over the degree 1. For example, if I have 1 over s squared and 1 over s cubed times something, and I make a partial fraction, the constant over 1 over s has to be positive. This is, we call this the residue. Alright? So we are saying that the function, if it has poles on the imaginary axis, it has to be simple poles. Simple poles means? Not power. So it's 1 over s. 1 over s squared is not simple. It's double pole. Right? If you have s squared plus w or plus 1, you have 2 poles on the imaginary axis. This is simple. If you put s squared plus 1, the whole thing squared, it becomes double poles. Right? So multiple poles on the imaginary axis. So this is what it is. If I look at it on the imaginary axis here, if I have 1 over s, it will be 1 pole. If I have more than 1, it becomes not simple. So the condition here, it says, if there is a pole on the imaginary axis or at an infinity, right, then these poles have to be with positive residues, and they have to be simple, not multiple. The third one, now we are no longer looking to s equal to a plus bj. We are looking to s equal to GW. Right? I remove the real part. Then I take the real part of G of IW and I found it positive. So basically what we are saying here, we are saying that we are replacing all these mathematical equations, which could be very complicated, to three conditions. One, a condition that is visual, basically based on the poles, all the poles are stable. Second, I look to what is happening at the imaginary axis, and I see if they are stable or not. Here, right? And poles at infinity means that the degree of the system are higher in the numerator, so we have poles at infinity. And then I go to the third condition, I just replace S by J omega, which means that I am in body diagram, frequency domain. And I look to the real part of G of J omega, and I see if it is positive or not. You are okay with this? This is very important for us because this is what will link the passivity theory to positive realness. So I would like you to understand this part. If you have any questions, just let me know. Because right now we are going to work only with frequency domain, G of I omega. Because we need, why we need G of I omega? Because we need the norm, the gain, like in body diagram.
Yeah, actually I didn't get why it's larger than or equal 0, because we have stability system, it's -1 in frequency domain. For example, in Nyquist. So when you plot Nyquist, you have imaginary and real. So the stability it's before -1.
Okay, you are
Why?
talking,
Why here it's larger than or equal
you are
0?
talking about the norm.
No, norm for G.
When you look to Nyquist, it's the normal phase, right?
Yeah.
This is not the norm, this is the real part of G omega. Has to be positive.
But sometimes real. Alright. We will.
You are okay with this? Yes? Alright, strictly positive real, what we are going to do, we keep 1 and 3, so this 1 and 3, we keep them, they are the same, they are valid, so we check there is no pole on the right hand side, we compute the real part, and we check that G of I omega A is positive, and then in order to make sure that it's strictly positive real, we replace number 2 by saying that the condition that G of S has no poles or 0 on the imaginary axis. Nothing on the imaginary axis.
Basically, the second point makes the system marginally stable.
Exactly. So the first one is telling you that the system is marginally stable. The first definition, system is still stable but marginally stable. But strictly positive real becomes the system is stable. There is nothing in the imaginary axis. For example, if I look to 1 over S, 1 over S, if I integrate this, I will get the constant. So if I put a system, for example, an impulse response, I will get a constant like this time. If I put double poles and I put the impulse, I will get the rump. So the system will go to infinity when t goes to infinity. So for bounded input, bounded output, the 1 over S is considered part of the strict positive real, but 1 over S squared, it's not. Everybody is okay with this? Let's do an example. Let's think it first and then we do example. This is another theorem that you have seen in your undergraduate, the Parseval theorem. So the Parseval theorem, it says the integral from minus infinity to infinity of ft squared. So f multiplied by f. So this is or y multiplied by y or u multiplied by u. Signal is equal to 1 over 2 pi, the integral from minus infinity to infinity of the Fourier transform of f of t, right? Or the Laplace, but replacing s by j omega or I omega. So f of I omega, so f is the Fourier transform of this f, multiplied by the conjugate of f, right? At I omega, d omega. So basically, this is the transformation from time domain to frequency domain. So from time domain to spectrum, power spectrum in the system.
Why we don't use directly Fourier transform? Why we go to possibility R? Because also Fourier transform take us to.
I don't need more than this. All what I need is this two. So here, for example, it says take the Laplace transform, f, the conjugate of f is f of minus omega. So take the integral of the Laplace transform evaluated as I omega multiplied by f of minus I omega, d omega, integrated from minus infinity to infinity will give you this signal here, ft squared. Is okay with this?
Also energy,
This is the energy.
yeah.
And we are talking about the energy from the beginning. So we are talking about passivities, we are conversion here. So if I take a system with input u, output y, and I integrate from 0 to infinity of y of t, u of t, then I know that y of t is basically the output of, or the effect of the system taking input u, right? So I will say this, according to Parseval theorem, is 1 over 2 pi, the integral of minus infinity to infinity of the Fourier transform of y, multiplied by the conjugate of the Fourier transform of u, right, based on the same definition that we have here. Now, y of I omega in the frequency domain can be written as g of I omega, the transfer function, multiplied by the input. So this will give me 1 over 2 pi, the integral from minus infinity to infinity of g of I omega multiplied by u I omega, u of minus omega over all the frequencies, right? And then here, this value of this result is exactly the same thing if I look only to the integral from 0 to infinity of the real part of g of I omega multiplied by u of I omega multiplied by its conjugate. Now this u of I omega multiplied by u of I omega is positive signal. If I talk about positive real signals, positive real systems, it means a positive real system means that y u bracket, which is this integral, is positive only if the real part is positive. Everybody understood that?
And also real, yeah. When you multiply u will u conjugate, it's real, not even.
Yes, it's real. It's in fact the norm.
So it's all real.
It's the norm in U in L2. Huh? So if we go back a little bit here, then we are saying the system is passive if this is positive. So u of y is positive if real part is positive, which means that the system is. So the system is passive if the transfer function is positive real. Right? So this is the link that we are making between them.
So passivity is equivalent to the stability of the system.
Passivity, we are going to use passivity to show the stability of the system. The system is stable. All right. So here the result that we are talking about, we are saying that if g of s, a transfer function, is positive real, then yu bracket is positive or equal to 0, which shows that the system is passive. So if the system is passive, it means it's positive real, and if it's positive real, it means it is passive. Now if I take the real part of g of s positive bigger or equal to epsilon s equals j omega in our case here, positive or equal to epsilon positive, it means that the system is strictly positive real. If the system is strictly positive real, then yu bracket, which is the real part of g omega, multiplied by u and u conjugate, can be written as bigger or equal to epsilon multiplied by the norm of u squared, because this is u times u minus 1. U passive. So this is input strictly passive, or input passive. All right. So now if I look to the real part of g of s, and I found out that the real part of g of s is bigger or equal to epsilon times the norm of g of omega. Right? So basically you look to your the norm of the transfer function. The real part is bigger or equal to epsilon multiplied by this amplitude, by the gain of the system. Then you are able to say that yu is bigger or equal to 1 over pi, the integral from 0 to infinity, multiplied by, you replace the real part by epsilon g of omega squared. G of omega squared, you can separate it into g of I omega and g of minus I omega, so you multiply by 1. You distribute it here, so g of I omega multiplied by I omega. G of minus I omega multiplied by u of minus I omega. And this will give you y multiplied by y conjugate. So we are able to show that if the system has the real part bigger or equal to epsilon, then the yu bracket is bigger or equal to epsilon times the norm of y squared. So all the results are coming from Parseval theorem. Right? And the trick is that the transfer function is passive, means the input, strictly passive means is the output that is passive, or the output system is passive. So this is an example here. We take g of s equal to s plus 1. So this is basically a transfer function where we have only 0. And then we replace s by j omega. Right? So we are going to write here j omega plus 1. Right, we can work on it together. So we have g of s is equal to s plus 1. S is equal to j omega. So we are going to have g of j omega is equal to j omega plus 1. So what I would like to know is to see if this function is positive real or not. Right? First of all, this function has no poles on the left hand side, so we are fine. Right? There is no poles on the imaginary axis. The pole at infinity, which is s, is simple, only one, there is no square. So we take the norm of g of j omega is equal to 1 plus omega squared.
Can you repeat the pole at the infinity? What is it?
S.
S?
Yeah.
Normal.
1 plus omega squared is the norm of the system. The real part is just 1. Huh? The real part of this system is just 1. The real part of g of j omega is equal to 1. This is the real part. This real part is positive. So we are saying that the system is positive real. Is it strictly positive? Yes, because it's equal to 1. 1 is bigger or equal to 1, which is strictly bigger than 0. So we are going to say 1 bigger or equal to 1, which is strictly bigger than 0. This is epsilon. Right? So this is strictly positive real. Right? Based on the results that we have done. Right? Is it output strictly passive? We cannot say because this 1 is not bigger than 1 plus omega squared. This is positive signal. In fact, this is the minimum the function can take. Everybody is okay with this? All right. Now, since by looking to the real part only, I will be able also to decide if the system is input strictly passive or output strictly passive. So in this case, the system is input strictly passive because it's bigger than epsilon, which is strictly bigger than 0. The real part. But it's not output strictly passive. Everybody understood what I'm doing here? Yes? Any question? Another example, 1 over s plus 1. So we have to help me do this. I always do the simple one, but the complicated one you do. So what should we do?
Same as.
Same. First of all, we have to check if there is unstable poles. So, any unstable poles? No. So the pole is s equal to -1. It's on the left hand side. Stable. Any poles at the imaginary axis? Zeros? No. Poles at infinity? There is no poles at infinity.
If we have an unstable zero or pause, what we will do?
So the system does not verify the condition, so it's not positive real, so we stop there. And we start praying to the course. There are other ways to do it, طبعا. Non-minimum phase system, etc. We have one ways to do it.
We have 0 at infinity, right?
We have?
We have 0 at
We have 0 at infinity here.
Doesn't matter.
It doesn't matter, it's simple 0. There is no pole at infinity. 0 at infinity, at s equal to infinity, the system becomes 0. How do you want to have it?
Infinity of time or infinity of s?
Infinity of s. Alright, so we replace s by j omega. So this is g of j omega is equal to 1 over j omega plus 1. So we multiply by the conjugate both up and down. So this will be equal to 1 minus j omega divided by 1 plus omega squared. So this times this conjugate will give you the norm of the complex number, which is 1 plus omega squared. The real part of of G of G omega is equal to 1 over 1 plus omega squared. And the norm of G omega is equal to 1 over 1 plus omega squared. Everybody's okay with this?
Due to the norm here, it's just real part.
No, the norm is
Don't need to use the transform.
you know how to compute the norms, huh?
Yeah, I know.
So 1 plus 3. What's the norm? Norm divided by the norm. So this will be equal to 1 plus 9 divided by 1 plus 16. This is the norm.
Yes.
Since we have 1 here at the top, so we have 1 over the norm of this, which is 1 plus omega squared. But in this case, the norm and the real part are exactly the same. Everybody is okay with this? Alright, so we look to the real part, so we know that this is positive.
Professor, in the previous example, we said that the real part of G omega is only 1, although the G omega is 1 plus omega squared. Only took 1. Can
The real
go
part,
back to
you're talking about the real part.
Yeah.
So we have S equal to J, 1 plus J omega. This is G of S. What's the real part of G?
I thought it was the part of the square, the norm.
No.
Actually, my question not.
Norm has no complex number. It's already real.
My question not how we can find the norm. Why it's square here? We don't put it square. It's norm square. Norm square. So norm square.
Norm square.
So
We didn't get the part of how we get the norm like
it's
that.
the denominator is 1 plus omega square or square or what this means square in norm.
والله ماني فاهم السؤال سامحني معلش I'm so sorry.
Square here we have G of G omega norm square.
Yes.
Square here it's
Norm 2. This is the understand the terms. Okay, this one is the norm squared here. This is what you're talking about?
yeah.
Yeah, this is the norm squared.
There should be a
Square root of all this.
square root, but we're not using
Yeah.
it.
Yeah, absolutely right. طيب يلا كملوا.
Now
We
it's
continue.
positive.
We need to check real of G omega.
So we found that the system has
Yes, sir.
no poles and complex plane, nothing on the imaginary axis. The real part is positive, so we are concluding that it's positive real. Right? Now for the strictly passive part, we need to replace the second rule, which is we need to replace this by the condition that the G of S has no poles or 0 on the imaginary axis. If we do 1 and 3 and we add to them 2, system is strictly positive real. So in this case,
Yes, it
it's a strictly positive real. So we are able to conclude that the system is strictly positive real. So we see this theorem makes it easy for us to check if the system is positive real or strictly positive real rather than trying to compute like what we did last time. طيب, so this is our example point here, yes? So we are concluding that it's strictly positive real. Then after that we look to the norm of G of W squared, this is equal to 1 over omega squared, and we compare the real part to this norm. Right? So the real part is 1 over omega squared, which is exactly the norm squared. So we can say that this is bigger or equal to epsilon times the norm squared. In this case, epsilon will be 1, and it's equal. So when I say bigger or equal, is this also true? So this system is output strictly passive. Right? Is it in? Huh?
I didn't get how we conclude that is.
So what we are writing is this. We are writing This is the real part. This real part is bigger or equal to 1 over 1 plus omega squared. You agree with this? You agree with this? So this is the norm squared. This one here. And the epsilon is equal to 1. And this is full. So this system is output strictly passive. But is it input strictly passive? We have 1 over 1 plus omega squared. This is the real part. In order to show that the system is input strictly passive, I need to show that this is bigger to epsilon positive. Right? Bigger or equal to epsilon positive. Can I show that?
For any epsilon.
For
For
any epsilon.
specific for any omega.
For any omega. So
Cannot be.
it cannot be.
Yeah.
Why?
Omega for true bigger values would go to
Will
zero.
decrease. Right?
Yeah.
The more you go, in fact, for this system, it starts at 1, and then it will decrease to 0. So you cannot show that it's bigger than a certain value epsilon. So we cannot conclude that it's input strictly passive, but we are able to conclude that it is output strictly passive. This is a first order system. We are okay with this? Mark, okay?
So the value of epsilon is 1 here.
Huh?
The epsilon is
Epsilon
1.
is not fixed.
Epsilon can be anyone. Give me any epsilon.
Give me anyone.
One is- Yeah, give me epsilon.
I can make it dependent on omega, no? Or I can't.
Okay.
Ah,
epsilon is constant.
it's a constant value, okay.
هكا وقت ما نلعب. طيب. Any other question? No questions? No. Everything is clear? طيب, this one is for you then. You do this for me and you let me know what you think.
I
Take it.
Yeah, I don't understand how it is output strictly positive.
How is output strictly
Yes.
passive? A system to be output strictly passive. Let me go back to the slide. Here. I need to show that the real part is bigger or equal than epsilon times the norm of the transfer function squared. If I show this, then the system is output strictly passive, and this is the proof. This is output strictly passive. You agree with this? All right. So G of J omega, this is the G of J omega. I took the norm of this. This is the norm, 1 over omega squared. I took the real part of this function. This is the function. The real part is this, right?
Yeah.
So it's 1 over 1 plus omega squared, which is exactly equal to the norm. So this 1 over 1 plus omega squared is definitely bigger or equal to the norm squared, which is this one, so? You agree with this? Because it's equal.
Yes, it is.
So the equal is still valid.
Yes.
And it's positive, which is because it's a positive term. So I verify the condition that I have there. So based on this condition, then the system is output strictly passive. The proof is done.
So here we take epsilon as 1.
Epsilon is 1. Okay?
But in input strictly positive, we take epsilon as any value.
Repeat this again.
In input strictly positive, we take epsilon as any of the values. We like
Epsilon, any value. Anything, but constant. Not function of omega. Yalla, everybody has to take a piece of paper and a pen. And let's work on this. S squared plus 1 over S plus 1 squared.
Can we see the previous time?
Repeat this again.
Previous time. For the first.
You took this one? Everybody took this one? Yes. This one you want? These slides are not available on your platform?
Right now,
No? Okay, I will put them in blackboard.
even the previous lecture.
والله انت دائما تشتكي يا سارة والله. طيب اوكي. I will put them back. So up to now we are looking to passivity versus positive reinforcement. Huh? And we would like to see what to do with this. There are very important theorems that we will see. The area of designing a system based on passivity is a huge area of research. It's a one way of designing a controller. Design a controller to ensure that the system is passive. أنا خلاص done with this.
You want to go with the next one?
I want you to put this so you can be able to work.
X squared plus 1 divided by x plus 1.
So I can at least answer is it positive real or strictly positive real, right? Based on the slide. Can we?
Suppose on the definitely contain no imaginary access pool. This is something
There
about
is a positive in the pose.
Huh? Just 1 second. Huh?
There is a positive in the pose.
It's positive in the pole?
Mhm.
What do you mean it's positive in the pole?
As in there is a positive value in the pole. There is one positive pole for this function.
And I have another example that I need to do with you, so we need to finish very quickly. I need to have some answers. Which pose you saying positive?
Yeah, when I computed the poles, I have negative
What are the
one,
poles?
negative 1, positive 1, and negative 1.
This one?
Yes.
It's only negative one.
Yeah.
Double pole.
Okay, I see.
سارة خلصت؟ ها؟ بس ما strictly positive real؟ أنا أعرف مش هشوف أسويها معاكم الحين. double pole it's not strictly positive real طبعا. يعني هذا condition 1 and 3 are valid, but the last condition here, no zeros on the imaginary axis. Right. So it's not strictly, it's positive real, but not strictly positive real.
اوكي انا احس بوزيتيف
لا.
لازم تلقى هذا اكبر من بكثير. لازم يكون اذا كانش اسمها نوم سكوير. اسمها نوم سكوير. نوم سكوير تاع نوم سكوير اسمه
Is it positive real?
No, positive real.
Yeah.
Yes, the real
No,
part is
because
real.
omega.
Is positive.
I don't know about omega because in the 1 minus omega squared. So omega is it's larger than 1, so it's negative.
Not everything is squared. It's squared.
No,
I'm not talking about strictly positive real.
Positive real are
Positive real. So the function is what? S squared
it's
plus
positive.
S squared plus 1 divided by
S plus 1.
S plus 1 squared. This is G of S.
We have
G-
negative 1, negative 1.
Right?
All that negative 1, negative 1, right?
The poles we have negative 1 but double poles.
Yes.
Double pole at minus 1. The zeros
No problem. Zeros we
It's
have.
conjugate. That's G omega
minus
minus G omega.
They're not double.
So these are zeros.
Yes.
These are the zeros, these are the poles. Everybody's okay with this?
Yes.
So the rule says that the system to be positive real, it has to have all the poles on the left hand side.
Yes.
So the poles at infinity and the zeros at infinity, they're simple. There is no poles at infinity and zero at infinity. The condition number 3, the real part has to be positive. We compute the real part.
The real part is
positive.
1 minus omega square whole square.
G of G omega
That's what happened.
is equal to 1 minus G omega. 1 minus omega square.
Omega
Plus,
square.
let's put here 1 plus G omega square divided by G omega plus 1. The whole thing squared. This will be equal to 1 minus omega square.
Yes.
Okay, yes.
Everybody agrees with this?
Yes, whole square.
Divided by 1 plus omega squared.
Minus.
The whole thing squared. This is the normal. This is the normal part is G omega, the whole thing squared. Multiplied by 1 minus G omega, the whole thing squared. Right? So this would be equal to 1 minus omega squared divided by 1 plus omega squared, the whole thing squared, multiplied by 1 minus omega squared minus 2J omega. Agree with this?
Yes.
So the real part of G of J omega is equal to 1 minus omega squared, the whole thing squared divided by 1 plus omega squared, the whole thing squared.
Plus 4G, plus 4 omega
Omega
square.
square, plus 4 omega
Plus
square.
4 omega square. You forgot it.
At denominator.
نعم.
Which one is this?
You forgot it when you multiplied by the conjugate. You forgot to.
Multiply by the conjugate, we get 4 omega square at the bottom.
In the bottom.
On the bottom. This is the norm. When I multiply by the conjugate, it's the norm. The norm term here, which is 1 plus omega squared, the whole thing squared. So I have 1 plus
4 omega square and the 2 minus 2 omega square it will cancel out. It becomes plus 2 omega square, so 1 plus omega square will be
So 1 plus omega j omega squared squared. The norm of this is the same thing as the norm of 1 over j omega plus 1 times the norm of 1 plus j omega plus 1, so? You agree with this?
Yeah.
This is equal to 1 over omega squared plus 1. I don't think it's good.
Yes.
So this is what I put here. You agree? You may have made a mistake. You may correct me if I'm wrong.
They actually multiplied.
Just multiply by the
And
cos.
simplify.
And simplified, yes.
Because they were to minus 2 omega square and then plus 4 omega square, so it will become a plus 2 omega square, and when you combine it, it is 1 plus omega square whole square.
Okay. So this is the real part, huh? So the real part is positive or equal to 0. So based on our definition, the system is positive real. Positive real. Is it strictly positive real? So to show that it's strictly positive real, I need to show that this is bigger than epsilon. So the real part is bigger than epsilon, which is bigger than 0. Right? The problem is this with this minus. So the function is always decrease. In fact, this function starts from 1, decrease to 0, come back to 1. And so I cannot find an epsilon where this function is bigger than epsilon to show that it's strictly positive real. So it's definitely not strictly positive real. Everybody agrees with that? Yes? So if I look to this function here based on omega, you will find when omega equal to 0, this function is 1. So omega equal to 0 is 1. This is omega equal to 0. The function is 1. When I look to omega equal to infinity, right? So this one is minus omega squared, minus omega to the power 2. So this is omega to the power 4. Divided by omega to the power 4, so it's again 1. So at infinity is 1. So this is omega equal to infinity. At omega equal to 1 exactly, it will give you 0. At omega equal to 1, it will be 0 here. So the function is something like this, whatever happens in between. So we cannot find an epsilon where the function can be bigger than this epsilon, and I say that it's strictly positive real. You agree with this? But there is one condition that we have in the theorem that can tell me that this is not strictly positive real from the beginning.
Imaginary.
There is the third condition. It says rather than looking to the pose at infinity, etc., look to, well, I put the graph somewhere here, so. I think
It's
maybe
the
I removed
middle.
it. I removed it. It's here.
The middle.
There are poles, there are zeros on the imaginary axis. So the replacement condition completely at the bottom is not checked. So it's not strictly positive. Everybody's okay with this? So we did it by mathematics, makes sense that it cannot find epsilon. But we did not have to do all this. By checking if there are zeros on the imaginary axis, we can decide if it is strictly positive real or not. Everybody's okay with this?
Please let